I believe we are live. Good afternoon, everybody. I hope you are doing well. Uh, let's see if I'm online. Let's see. Yes, you're live. Uh, so this is part 5 of dynamic programming running. Yesterday we left our session on just on this ideas that there were 4 ways to solve what should I say? Um, yeah. So there were 4 ways to solve that problem where we are allowed to pick any element and basically maximize the sum of elements that I pick in an array such that I do not pick adjacent elements. Kind of the, like, if you know from previous sessions, kind of like the house robber situation, but we kind of discussed how to define states and based on the definition of states, how to define transitions. Let me just do something here. Uh, Maybe I can reduce the resolution. Otherwise, this is actually affecting the quality of the data being streamed without. mm, Let me just see. I think this will be better because the resolution is lower and the data that is being streamed is lower. Okay, so we were on this. Today we will try to discuss, before going on to further questions, maybe discuss about time and space complexity associated with definition of dynamic programming solutions. So this is going to be the part 5. So how to define, uh, let's say, time and space complexity of DP solutions. For example, let's say you have defined some states, so maybe dp of I equal to dp of I minus 1 plus dp of I minus 2. So this summation is a constant time taking thing, right? So here in this case, every transition takes constant time. So in this case, my time complexity will be just the number of states. For example, you have, say, 3 loops, I from I from 1 to n, j from 1 to n, and maybe k from 1 to t. And within that, you can say the dp of I, j, k equal to some constant time, maybe some addition, some subtraction, some maximum, some minimum. Basically, there is no further loop. So this is another order of one operation. In this case, again, the time complexity is the number of states. Here, what is the number of states? ijk. So kind of a 3D cube of size n by m by t. So time complexity equals to order of n m t approximately. But what you have some transition, let's say I goes from 1 to m, let's say m, j goes from 1 to n, and let's say I define dp of ij equal to, let's say this is a series of steps. Maybe I go from, let's say, uh, let's say I define something maybe maximum of all the elements. So maybe maximum, even though this will not be very useful, but let's say maximum of v0, v1, v2, vn. Assuming 1D array, but we have 2D based transition. So in this case, you see, maximizing these n elements is an order of n operation. Of course, you cannot define this directly. You have to mention a loop within that. Just yeah. So in this case, this is an order of n operation. You have to do it like it will take order of n operation because you will initially take some minimum value, and then you will go to every element and you will see that maximizing that. So for example, you can take a very high value by ln max, and then so initially, or you can also take the first element. Not necessary you have to take the ln max. And then from the second element, you can go up and maybe mention that. Just give me a minute. Yeah. So you can take the first element, and from the second element to the end, you can just say that my final new answer is the maximum of previous answer at this current element. So this is a kind of an order of n transition. So transition time, I should say. So in this case, my time complexity is this is the order of n into m into n again because every transition takes order of n time. Space complexity does not change because GPIJ, I should say auxiliary space, because we are not considering input and other. In space complexity, we always consider the extra space that you have used, not considering the inputs and outputs. Here, in our case, the auxiliary space that we have taken is n multiplied by m because we have that many DP states that we have externally created to solve our problem. I hope this makes sense. So, can I say that time complexity is number of states multiplied by time taken by each state? Now, this definition is kind of a little bit vague. Why? Because sometimes the time taken by each state will be dependent on the state number. Like, for example, what if I say that here I want max of V0, V1, V2 up to Vi, or maybe up to Vj. So that means in this case, the average or the transition time also depends on the state. So J can go from 1 to n. I can go from 1 to n. And I am transitioning from 0 to Vi or maybe Vj. And in that case, you can consider the average time, like maybe 0 to n by 2, if it is I case, otherwise 0 to m by 2, right? So m by 2 time it takes. Maybe you can consider the average. So, so if it is dependent on function of state, uh, then try to take average. Sometimes it helps. Otherwise, you can try to devise some formula if you can. Usually, taking the average or taking the maximum bound also gets you to the answer, right? Let me show you an example. So consider this only. So maybe this oblique goes on V of I in this case. So can I say that this is a uh, like average which will take from n by 2, average is order of n by 2. That's why we're saying that, okay, so time complexity is order of n cross n by 2, which is approximately order of n squared. I hope this makes sense. Okay. Sometimes you can get weird equations, like maybe here, maybe here you can have order of, you can think of it like maybe Vi plus V of I by 2 plus V of I by 4 plus dot dot dot. So it's like log of I. So you can say log of n by 2, log n. So in this case again, that time complexity, time complexity will be order of n cross n cross log n. Here, of course, the average will not be n by 2, it will be log of n by 2. Because on the average, we are going up to n by 2. And we have logarithmic depreciation, right? Like if we assume that I by 2 to the power k equal to 0, then or 1 I should consider to be the last thing, then k equal to log n. Approximately, right? Where k is the number of steps. Not exactly log n, I should say log I. So I. But again, we have considered that I is average. So it's like I. So I by 2 to the power k equal to 1. So it will be log I, and I we have considered as 10 by 2 on the average case. So this kind of tricks you can apply. Basically, you want to calculate the number of states into some approximation of time. taken by each step. Okay. Now let me give you some questions. Maybe this will help you out. Let's say let's assume let's start with a simple question that dp of I equal to dp of I minus 1 plus dp of I minus 2 plus dp of I minus 3. Kind of like a Fibonacci series. And I goes from, I should say, 0, as we said, 3 to n. So try to calculate the time complexity and space complexity. Try to give 1 minute of time or 2 minutes of time. Okay. Okay, let's get back to this. As we can see, this is order of n multiplied. This is just order of n because time complexity of calculating this is constant. Okay, uh, and the space complexity is again order of n because we only have a one-dimensional map. I hope this makes sense. Okay, now let's tackle some higher problems. Let's try to solve. Let's say I from 1 to n, j from 1 to n, dp of ij equals to dp of n plus dp n by j plus dp of n by j square plus dot dot dot. Try to compute the time complexity and the space complexity of this problem. And this is a good problem, so maybe give 5 minutes. Sure. I hope you have given enough time. Let's try to solve this now. So we are traveling from n to n by j plus n by j square plus n by j 2 to the power 2, sorry, 2 to the power 4, basically multiplying every time. This approximates to log n, I should say. I should not say log n directly. I should say that maybe log of n by 2. That j is kind of like almost constant. If j is estimated as n by 2, then this will be, uh, I should say, this is not 1, then 1 square, then so maybe by so 1, then 1 by 2, then 1 by 2 square. No, it is directly taking the value of j. So constant, right? So that means time complexity will be order of nn, which is the number of states, and space complexity will be the same. This idea was very important, that this is not log n, this is constant. I will try to give you a small proof that how so proof harmonic series, not exactly harmonic series. Let's say try to approximate. So say n by 1 plus n by 2 plus n by 4 plus n by 8 dot dot dot. This is log n, exact, almost exact. But here we don't have n by 1, n by 2. We have n by j plus n by j square plus n by j cube dot dot dot. So can I say that, or did I mention that? Yes, let's say j to the power 4, j to the power 8. Let's do it for this case. We can prove that those are almost equivalent. Let's say, can I say that the nth term is n by j to the power k, 2k? Or I should not say that j by 2 to the power k. I should say j by 2 to the power k. This is kind of the kth term. So the first term is j, and the second term is j square. Third term is j4, right? And we can assume this to be 1. So can I say that this is log n? This is 2 to the power k log j. J I will assume as log n maximum. So this gets cancelled. So 2 to the power k equal to 1. So k equal to log n. Uh, oh, no, 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 not that. 2 to the power k equal to 1. That means I can say that log 2k equal to 1. So k is some constant. I hope this made sense. Now let's take the exact case that n by j plus n by j square plus n by j cube plus dot dot dot. In this case, the nth term is n by j to the power k, right? So j I will assume as order of n only. So this is, if I assume as 1, then can I say that log n equal to k log, so can cancel. So k equal to 1, which is constant. That's what I want to mention. So constant. So I can only go up to constant number of terms in order to get this. Now, before we proceed further, I will give you some reading articles, and I will try to prove some results about prime numbers, factors, divisors. How many are there? Like, so this is going a little bit off topic. This is purely mathematical, but let's try to analyze some good results that are helpful. So question, how many prime numbers are less than equal to n? So up to n, how many primes are there? So this is defined by a theorem called PNP, or prime number theorem, which says that number of primes. So number of primes has a up to n has a good name. The function is called pi of n. So pi of n, which is number of primes up to n, is approximately n by log n. This is the prime number theorem. If you want a better approximation that you can probably use in Codeforces, better approximation is n by log n minus 1. It goes very close. Like try for 10 to the power 5, 10 to the power 6, 10 to the power 3, 10 to the power 7. Try number of prime numbers. Compute by Shiva-Barathe's theorem, and then cal calculate this. You will see the answers are very close to each other. Okay, this is the first conclusion. Okay, now there is also one other conclusion that is kind of derived from the same idea. Let's say I pick a random integer. So pick a random integer, like from 1 to infinity. Pick any random integer. What is the probability that that integer is prime? That is approximately 1 by log base. Uh, so pick a random integer I. So, so the probability, so P of I equal to prime is approximately 1 by log base E of I, or a better approximation 1 by log base E of I minus 1. This 1 is outside, by the way. So this is another conclusion from prime number theory. Okay. Next, I will try to prove that how that 1 by 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 plus 1 by 5 plus dot 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 harmonic series is approximately equal to log n, where n is the number of terms. Uh, what you can do is calculate it for very high values of n. 10 to the power 3, 10 to the power 4, 10 to the power 5, 10 to the power 6, 7, and calculate log n. You will see that the difference approaches some constant. It's about 0.5527. This constant is called Euler-Macaroni constant. You can say this is from 0 to infinity, 1 by floor x minus 1 by x dx. So this is log x, of course. And this is kind of my harmonic series. Of course, exactly 0 it's not defined, so maybe 0 plus. But it's not necessary because we don't really care about integration at solid points anyways. So maybe some ideas. You can try to compute this integral from very high values of n, and you will see that the answer is kind of like what's the notation for Euler-Macaroni constant? Yeah, gamma. That is here. Yeah. So this is kind of the approximation of harmonic series. So you can literally write harmonic series equal to log n because the difference approaches a constant. Of course, since this is log n, if n tends to infinity, it tends to infinity. So this also proves that harmonic series is divergent in nature. Okay. Now let's talk about divisors or the divisor function. So there are a lot of approximation. So what should I number this? Uh, Maybe a question. Uh, what is a divisor function? It's like let's say I give you an integer n. Question: how many divisors are there of n? Now there is no direct answer to this. Some people compute it with order of root n complexity. Like since divisors come in pairs, uh, one thing I want to mention, this is the divisor function. Uh, Higher variance of this is not very important, but you can look it up. Uh, let's search in Wikipedia or Google about divisor function. Like how is sigma 0, sigma 1, sigma 2, these defined. But again, this is optional for comparative coding. I spent some time learning about those. Did not really understand much, but got a good intuition. Maybe tried out some values, brute force it, stress tested some values, found them approximately correct. could not really arrive at much conclusions. If you can, if you also go through it, maybe get some insights and maybe conclusions that may be useful in competitive coding or good knowledge in general, please write that down in comments, or maybe some better articles to this teaser function that can be helpful in order to understand it. Then please do let me know that. Okay. Now let's try to solve some simple questions. Let's say dp of I equal to uh, loop for primes up to I. Like if I is a prime, then I will run a loop for order of n, and I goes from 1 to n. So what's the time complexity? And what's the space complexity? So give 5 minutes. Try to use the prime number theorem. Try to use some of the conclusions. This is not very difficult. Okay. So let's come back. So look for primes after n. Uh, Sorry. So we'll come back. So look for primes up to I. So it's like number of primes up to I is approximately log of I, like I by log of I. And we can approximate I as n by 2, right? So it's like n by log n. And then also n for number of states, which is rank complexity and space complexity is order of. So this is the number of primes. Also, I wanted to mention some results from the divisor function. Like you may see in that article that this is written that number of divisors g of n equal to some e to the power uh, log n by log n times some constant, maybe let's say p. So this is very small, it's equal to, I should say, approximately. And p is some constant. So like I should say that, for example, let me just say that. Like, for example, if n is up to 10 to the power 9, then dn is approximately 10 to the power 3, kind of. So that's a way of thinking. If n is up to 10 to the power 12, then dn is approximately 300. So if we do a cube root, so cube root of 9 is around 10 to the power 3. So it is kind of correct. If we do cube root for 12, it's 10 to the power 4. But you see, this is much smaller. You can try to brute force this for some values, like, but see, higher than 10 to the power 12, I don't think you can do it directly because first you have to mention that n equal to p1 of A into p2 of B, like p1 of A1, p2 of A2, uh, p3 of A3, right? Dot dot dot, pn of an. Then the answer is A1 plus 1, like bn number of divisors, of course, A1 plus 1 times A2 plus 1. Basically, I should say pi of AI plus 1. So, and here you can maybe calculate what is the value for this. Like, you can maybe try order of n to the power 1 by 4, order of n to the power 1 by 3. But still, it will still be slower. Like, you can say that it is somehow bigger than n to the power 1 by 4, is dn, and n to the power 1 by 3. Maybe you can try this if it satisfies for up to 10 to the power 18. Like up to 10 to the power 12, it satisfies. Because n to the power 1 by 4 is 100, or let's say 10 to the power uh, Sorry, it is not 10 to the power 3, it is 10 square. So 100. So 9 by 3 is around 10 to the power 3. So not correct. And 9 by 4 is around 2 point something. So yeah, but still small. So 1 by 5 maybe. Like 12 by 4 is 3, but still smaller. So you can, this is a very, the number of divisors is very less for a usual number, but there are some highly HCMs. Uh, they are called HCMs because these are called highly composite numbers. They have very high number of factors, kind of like 12 or 64 or maybe 128 or 150. No, not 150. 153 does not divide. So basically, a lot of factors are there, like 2 to the power a into 5 to the power 3 to the power b into 5 to the power c, and none of them are zero. So that in order to maximize this DN, we try to maximize this AI, so such that the product is maximal. So those are called highly composite numbers. So you may get some outliers, but usually you can say that number of divisors like Dn is approximately order of n to the power 1 by 3 only for CP purposes, comparative coding purposes. There is a Codeforces blog. Uh, it's blog. Like the entry is 651. This is in Russian, so translate to English. And then he has mentioned how n to the power 1 by 3 kind of works for a lot of situations. But again, I should mention this is not the real result. This is very close to the real result, e to the power log n by log n. But computation of this is not really practical in Codeforces type situations, I believe. If you find a better approach, please do let me know. Okay, this is what I wanted to mention. So we have learned about divisor function, how it is approximated to order of n to the power 1 by 3. We have learned about prime number theorem, probability of a number being prime, a harmonic series, convergence. So I will keep this session up to here. Maybe learn about or maybe explore about these topics. The the mentioned blogs and links will all be in the description. Thank you very much for watching and like, share, subscribe if you find value. And goodbye.